Hello and welcome back to the Oxford MAT Admissions Test livestream, coming to you from the University of Oxford. My name's James, I'm the Admissions and Outreach Coordinator for MAT at Oxford, and on today's show, integration. So this is a MAT show broadcast from the University of Oxford, where we're looking at some maths topics. They're all drawn from the TMUA specification. That's an admissions test that Oxford is using for maths admissions and computer science admissions. And we are going to look at some past TMUA questions as well, but we're also maybe going to learn a bit about integration and maybe get ready for integration questions in other settings as well. Hello to Ginger and hello to Pecky, and chat is running with Beth as well. Beth is a third year student at New College. She is here to help run chat and make sure everything's going well there. You can also talk to Beth if you'd like to talk to an actual Oxford student. If, for example, somebody has asked, "Dear Beth, did you sit TMUA back when you applied?" We will find out. I pretty feel like I'm setting Beth up to be asked anything. Sorry, Beth. Hi to Mary as well. Good. And who else is here? Let's see. Hello to... here they come. Anonymous has reminded me that you can be anonymous in Slido chats. One of the reasons we use Slido. Hello to Quackers and EJ. Pecky would like to know about the trapezium rule, which I've seen a few times. I think I haven't picked a question, but we saw one a couple of weeks ago with the logarithms. We saw a question about the trapezium rule. Definitely worth knowing, definitely worth thinking about, because thinking about stuff's good for you. Hello, Ginger Biscuit. Right, another reason that we use Slido is that I can do polls like this. The stream features a certain amount of voting. At the moment, they are voting for how their day is going today. Yeah, let's find out. But we also use the stream for voting for which questions we're going to do. Time for a little bit of scrolling. Because you see at the top here, I've got a kind of worksheet that you can get as well, so that rather than waiting for me to scroll down and look at the revision notes, or scroll through this page of information about integration, or scroll through this page about the trapezium rule, you could get this as well on the MAT Live website. There's a link written on the screen right here, or there's a link in the YouTube description, or if you type Maths Admissions Test Livestream into your favourite search engine, or dare I say it, your favourite LLM, then maybe they will give you the link to get to that homepage, which has got all the worksheets for previous episodes and this one. And very soon it will have the worksheet for next week's session. I've been trying to be 1 week ahead, but just like last week, the sheet is finished. It is just not passed. It has not passed quality control. So I'm going to make it good and post it tomorrow. We're going to do some revision questions in a bit, but then further down there are TMUA questions as well. So let's zip that back up to the top. Chat's having a really good day. First off, there are loads of you here. Hello, everyone. I don't know if you've found out about the stream recently or something like that, or if you've just joined in because, hey, exams are done, right? Time for summer. They are also having a pretty good day. There is actually nobody on 1 star, which is, I'm always looking out for people who vote for 1 star and 2 stars, right? Because they're having a pretty terrible day. There's one person I see them on 2 stars. I hope their day gets better. Right, who's in chat? What have I missed? Yeah, I know, LLM's like crying emoji, right? Like, I have to worry. Like, one of the reasons this is still called Maths Admissions Test Livestream, rather than changing name. You know, we changed which test we're using, but we've kept the name. And one of the reasons is because your favourite LLM is indexed from 2024, when this was called MAT Livestream. So I think I'm making things easier for your large language model by calling it the same thing now. Somebody recently asked me why I'm not calling it TMUA Livestream, even though it says TMUA all over the place. Partly it's because it's harder to say TMUA. Partly it's to try and keep all the links happy. Things you've got to worry about. Hello, Erica. How are you doing? And what does Dexter say? Welcome back, Dexter. Right. He's here from GCSE. There is a significant number of people, they're not always in chat, but there is a significant number of people who haven't seen any A-level maths yet who are using this as a way to find things out. Peggy's having an amazing day. They wanted to vote 6 stars. Hello, Alfie and Alex, and definitely not +C. What a great username. We're definitely. I'm going to have to work that out in a second. We always start with a bit of a question. This one is not TMUA. This is a question from a summer school that I run. So I'm using it here just for fun. Here's a question with an integral in it. And the reason I like this question is it tests a little bit your understanding of what a definite integral actually is. And so I've got a definite integral on the screen here, look. Here it is. There's one. Definite because it's got numbers, 0 and 1. And it's got this dummy variable t that appears here. That's not super important. If you would prefer it to say x here and here, you can replace those with x if you really want to, but it doesn't matter, right? Because it's a definite integral. I'm sort of testing your understanding a little bit just by saying that. Right, but we always start with the maths, so we'll stick that up there, and we'll see if anybody's got a way to get started with this. Hey, Matt GCSE, you don't. I should say you don't have to tag yourself as GCSE student. So like, I'm worried that I'm sort of branding people now. Oh dear. Okay. Right. You can also be anonymous, of course, if you want to. I have to assume everyone is giving me names and information because they want to. Oh, good. Okay. Becky says, I don't like recursion. Yeah, it looks a bit recursive, doesn't it? Because it's this function which is defined in terms of 1 plus something times, oh no, it involves the function itself. But actually, you've met recursion like this in other places before, without even really thinking about it as recursion. We will see. Yes, good. Okay, did Beth actually answer the TMUA question? Let me find out. I kind of want to read it out if you did. Maybe you didn't. Oh, you did reply. Beth says that Beth did do TMUA, but don't ask me what I got. Fair. Okay. Right, okay. Interesting observations. What can we do? Oh, yes, this is a true fact. Thank you. F of 0, true fact. If you put 0 in here, then who cares what this integral is? It's multiplied by 0, so you'll get 1. That's true. That makes me happy. And then an anonymous person has given me, I think, the whole solution at the top there. Good. Okay. The thing that I'm testing really is, although this looks like horrible recursion or something, this integral that I circled, it's just a number. So definite integration takes a whole function in some region, but it's quite greedy. It takes that whole function and just returns a number. So it's not a function of x, it's not a function of t, it's just a number. If the function is positive, then this represents an area, and this is a little diagram that people sometimes draw to say, oh, here's your function, and here's the area underneath. But that is only an area if the function is positive, which is kind of an awkward fact about area that I'm going to try and come back to, I think. But this is just a number. Let's call it A. Let's go and check. It's not so scary if we just call it A, because then look, so once you've decided that all of that box is just a constant, f of x is just 1 plus ax. So then you can get this like f of 0 must be 1 because it's just linear and it goes through 0, 1. And then I guess the thing that we just need to know is A. Oh, you did a math summer school, but I was doing a different math summer school. Ah, which one were you doing? I would have come to give a talk, but I was doing my own summer school. Which one was that? I think I remember being invited to a math summer school and I had to say, sorry, I'm already doing simultaneous summer schools. Good fun. So we've got this, and I guess maybe this is recursion. But now that we know f of x, we can plug it in over here. And time for a little bit of integration. I'm going to zoom in, but I've got this kind of thing. I guess this is technically recursion because it involves an a on the left-hand side and an a on the right-hand side. A is being explained in terms of a itself. If I zoom in, this is the integral from 0 to 1, so I'm going to put my square brackets, and I'm going to put a function in here. The rule for integrating a power of t with respect to t is that you increase the power by 1 and you divide by the new power. So here I write down at squared over 2. You keep the number the same out the front, the coefficient the same out the front, but you increase the power, or the exponent, by 1 and you divide by the new exponent. It's important that you do not try this with the exponent minus 1, because then adding 1 would give you 0 and you must not divide by 0. Anyway, here's some numbers. So this turns out to be 1 plus a over 2. And so if I remember what was all the way over here on the left, it was a. Then I've now just got an equation. So my maths now reads a is equal to 1 plus a over 2. And I guess you could still think of this as recursion. It says a is 1 more than half of a itself, but probably no one thinks of this as recursion. You just think of this as something to solve. So a is 2, and f is 1 plus 2x. Oh, sorry, f of x is 1 plus 2x. Weird. You find a function instead of the function. Oh, that is a bit cheeky of me, isn't it? Sorry. Yeah. Turns out there's only one. It's a unique solution. I've been doing that all week with the summer school that I've been on. I've been asking them to solve equations which might have one solution, multiple solutions, or no solutions. And I've been a bit lazy. I've just been saying find all x. And I use the phrase find all x. Find all x with x squared equals minus 1, right? And the answer is no x. Everyone seems to find this quite uncomfortable. People don't like it. I need to find a different way to say this, because in my head that works, right? In my head it's like find all x with x squared is minus 1, and you're like, job done, there are no such x. We found all none of them. But people seem to not like that very much. How do you integrate 1 over x? Yes, okay, you can't. For the purposes of TMUA, you cannot integrate 1 over x. The TMUA spec is a bit limited. Let's have a quick look at it. I'm just going to hide chat. I can still see you, don't worry. I can still see you. Oh, actually, can I? Ooh, there we go. I can still see you. Oh, no, I need to. Faffing around. You can't even see what I'm faffing around with. Okay. In the TMUA specification, the only thing that you're required to be able to integrate is that second bullet point up there. Finding definite and indefinite integrals of x to the n, where n is rational and not equal to minus 1. And that's it. That's all you can integrate. So I've got in my revision notes, I've got down here, the indefinite integral of that is over n plus 1. And that's it, provided n is not minus 1. And you do not find out the thing that Red has said, which is, and Emma has said as well, that it involves natural logarithms. Oh, good job, chat. Look. This is another example of chat knowing more maths than the TMUA specification. We've got to remember this, by the way. The TMUA specification, the spec for this test, is based on not all of the maths that you know, whoever you are, because it's the kind of greatest common divisor of the maths that everyone knows. It's the maths that we think everyone has seen at that point, whatever order you're doing maths in. Which means that loads of you know this fact about natural logarithms, but some of you don't know what a natural logarithm is, and that's fine. The test is designed so that even if you're doing, I guess maybe you're doing maths and further maths in parallel, both at the same time, in which case you might not have seen natural logarithm yet. So not only does the question make no sense, how do you divide by 0, how do you integrate 1 over x, not only does the question make sense, the answer makes no sense as well, right? It doesn't help Isaac Newton has turned up at the top of chat to be a sort of Easter egg. I don't think Isaac Newton can take credit for that being the answer to that differential equation, but you know, yes. Yeah. Quite possibly. I might be Ginger Biscuit. A-level. Is this a new thing? That's a combination of memes. They've been here a few weeks now, and their name is now a combination of the time that everyone set their username to be their favourite biscuit, combined with the time that everyone set their username to have what qualification they were studying, which was just now. Right, memes collide. Up there with Lewis Hamiltonian, which was the time everyone was an F1 driver and the time everyone was a mathematician, and somebody set themselves as Lewis Hamiltonian, which I found very amusing at the time. Right. Yes, Beth's been on Maths Club. On this channel, if you scroll back far enough, you can find episodes where I have Beth on screen as well. Beth's doing a great job in chat. Right, I feel bad now. Hogging all the screen time. Good. Okay, am I being useful? No, I'm not. Right, that was a question involving an integral. Great fun. Time for, I think, some of these revision notes quickly. Let's hide chat again. You need to know 2 sorts of integration. You need to know about definite integration, which is the one with limits. But when you learn about the integral of x to the n, it's easiest to learn about something that's called the indefinite integral. And one way to think about this is it's just a fact that's on the specification, where the indefinite integral of x to the n is defined as x to the n plus 1 over n plus 1 plus a constant. That's maybe not a very satisfying thing to think about, though. This idea that's like, oh, it's not even defined, up to a constant. You get this plus c, where c is an arbitrary constant. The idea of that, of course, is that if you differentiate that expression, you know how to differentiate powers of x, you get back to x to the n. There is another way to think about indefinite integration, which I would like to show you. It's hidden in the notes. Let's come down here. It's the one that says the integral. This is the bit where I can't read my own notes, even though they're on screen. The integral, yes, this one, with constant a is worth thinking about. So this is the integral from a to x of some function. Can you see this one? There it is. It says it's worth thinking about. I claim that's worth thinking about because it's a function of x. As you change x, you get different definite integrals. If we imagine that f is a positive function, you get different areas. Split screen on this. So if just to make things easier, if f is positive, then you fix a and you change x. If you do that, then as you change x, you get different areas. I guess as I increase x, I get more and more area for this positive function in this nice easy world, I suppose. More area because I'm increasing x. Which we've got a function of x, which I claim is the same function that you might write down if your job was to write down the indefinite integral, which is sort of mad because it's definitely a definite integral, pun intended, because it's got limits, a and x. But it behaves like an indefinite integral. There's this result that says that if you differentiate that, if you take this expression for the area underneath this positive function, you take this expression for this area underneath, which is changing with x, and you differentiate, and the value you get is the function. You get back to the function. And that's called the fundamental theorem of calculus. It is not obvious. It's something that gets drilled into you in school, I think, if you do A-level or equivalent, I assume, that differentiation is the opposite of integration, and that when we write down this indefinite integral up here, our whole job is to write down x to the n plus 1 over n plus 1 because that differentiates to x to the n. But it's not obvious that that's even what we want. If we're talking about area or something like that, it's really not good. I guess it doesn't help that at A-level we don't really have a working definition of integration, and we don't really have a working definition of differentiation. You sort of have to do a maths degree at university if you want to find out really what's going on there, or read the material outside of doing a degree. You need a lot more sophisticated mathematics to understand really what's going on in general, not just for powers of x, but for other functions. Why is integration the opposite of differentiation? Crazy. Yes, okay, so the value of a, the value of a in this one, if I come down, good chat going on about a. The value of a down here in the lower limit sort of matters. If I make a different choice of a, then I get different values for the function. But it's just like the constant plus c. If you had some capital F, if you had some capital F, if you know capital F of x with derivative equal to little f of x, then this would be big F of x minus big F of a. That's how you do integration, right? You might draw these square brackets and you might say, aha, I know something that differentiates to that. I know how to integrate this function, you might say. I'll do this and then I'll plug in the limits. So this f of a plays the role of a kind of constant. I just think this is fun to think about, right? That these things are all related. I guess I'm encouraging you to play around with this thing called the fundamental theorem of calculus, which is in the specification. I think when I learned about integration and differentiation in school, nobody ever said fundamental theorem of calculus. I wouldn't have recognized it from that name, I think. At university, I have strong feelings about fundamental theorem of calculus. I think it's great. I have a sticker on my water bottle that Beth gave me this sticker, right? Beth in chat gave me this sticker. It says, it's a pun, It's from the Women in Maths Society at Oxford. It says, girls just want to have fundamental theorems of calculus. Because at university we've got more fundamental theorems of calculus. We've got better versions of that fact. Big fan of fundamental theorems of calculus and stickers. Right, what's going on? Somebody asked what's the definition of integration on TMUA, and there is none. There's not really a definition of integration on A level as far as I can tell. That's fine. Don't worry about it. Don't worry about it. Okay, what sort of ODEs? This is a good question. So they're asking about differential equations because differential equations are on here. This is the only sort of differential equation that is on TMUA. And I think they use the phrase, yes, they use the phrase differential equation. So the solution is to dy by dx for the derivative. If you're told that that's f of x, then to undo the derivative and get back to what y is, you're supposed to integrate both sides to get back to some function. You can only actually do that using TMUA specification, like work out the function, if f of x happens to be some powers of x multiplied by constants and added together. But because you only know how to integrate x to the n and combinations of those, there's not very many things that it could be for you to actually solve that. There's not very many differential equations. And people in chat really are talking about logarithms and signed areas. Yeah, it's tricky. None of which is on TMUA. There's an uneasy relationship between integration and area that I'd like to mention. Now, you're very careful students, I know, so you never mix this up. But here's the rule. If a is less than b and the function is positive, so if you have something, I've drawn this picture before, I'm going to draw it again. If you have some function like this and you have a and b, then integration works out the area between your function and the x-axis between a and b. It's surprisingly hard to write all that out, right? Maybe I should just draw a diagram to show you this area, which is kind of surprising, I think, because there's no definition at A level, so everything's a bit surprising. But you have to be a bit careful. If your function is negative, then you'll get a negative number. And areas are supposed to be positive. There's this concept of something called signed area. So I'm going to scroll slightly. And so if you integrate, you get a negative number. So the area is this. Good chat comment. Let's go for chat. Are there functions that you can't integrate? I don't mean us, I mean anyone. Yes, there's kind of two serious answers to this. There are functions that you can't integrate in the sense that you can't write down a nice looking function that is the answer to the integral. And there are also functions that are too badly behaved to have an integral. If your function is not continuous, then you've got to look quite closely at it. But nobody knows. My notes are messed up. Thank you. You put it in brackets, but that's kind of just as important as the stuff other people are saying. Check the web. I had some trouble. Is it all centered? Occasionally it all gets centered. Is it worse than that? I had one point where I had an expression less than u as a maths expression, but it got converted to the start of an HTML tag. I don't know if anybody knows HTML, but angle bracket u close angle bracket, they use that for underlining text. So instead of saying something was less than u, I said underline all the rest of this document, and then I couldn't get rid of it. People say badly behaved, and there's some technical conditions that it's easier to just summarize. It's like well behaved, badly behaved. I'm definitely not going to tell you terms and conditions now for whether functions are integrable or not. It's spoilers for the university content, right? Which you could go and find out. It's pretty tricky. Okay, Yeah, okay, chat's having a go at that as well. If you do integration blindly without checking if the signed area is positive or negative, will you get the wrong answer? Possibly. I mean, you'll notice when you get the final answer, if you get a negative number, you'll know that something has gone wrong because areas are supposed to be positive. The case that I'd like you to be really careful about is ones like this, where you're trying to find the total of these areas. Because if you just integrate, then you have some region over here where your integral will be positive, kind of because it's adding up little positive contributions to the integral. And you'll have some region over here where your integral will be negative, and they will start to cancel each other out. They will positive contribution and negative contribution, they will give you some sort of random number that's a combination of that positive and negative thing. Not actually random, I shouldn't say that unless I mean it. When what you probably want is you want the integral of f up to c, so this is a and b, you probably want this, and then for this bit, you probably don't want that, you probably want a minus sign. Because if you just integrate, you will get a negative number for that bit. And part of the challenge here is to work out, well, what's c? Where does this happen? So if you're not careful, then you'll get the sum of those things when probably you want the difference. You want to subtract this negative contribution. And those are the ones where you want to be really careful. The question will make it obvious, I think, that this is what you want, because they will probably say total area of the regions, like this. Because in some sense, if they just say area, maybe they mean signed area when you set them up. You can't integrate sine on, I know I picked a terrible example. You can't integrate cosine on TMUA. You just don't know what the integral is. But if you just do the integral of cosine, then you get some positive bit, some negative bit, and you get some positive bit, and you get back to 0. The integral of cosine x from 0 to 2 pi is 0, because these things cancel out. The area is not 0, right? Because for the area, I should do this very carefully, and I should stop at pi by 2 and put a minus sign in for the next bit. And then I should stop at 3 pi by 2 and start putting a plus sign back in again. Are these integrals that I'm doing area or negative area? That's on purpose, because like front of hands, back of hands, it's like turning it over as well. Cancelling out. Your hands are a bit like sine. Never mind. Let's not do the analogy. It's not a very serious analogy. Can we integrate non-continuous functions? Not for TMUA. In general, yeah, but you need some framework for what you're doing when you do that. In general, can you find areas? Let's talk about this more generally then. So, if you have some function that's maybe like a series of triangles or something, that's going to come up in one of these TMUA questions. 1, 2, 3, 4, 5, 6. And you're told this is f of x. You haven't been given a function. We haven't been given like an expression for f of x. And you want the integral from 0 to 6 of f of x dx. Well, this function is definitely positive, so that's the area. That is this positive area in here. So in some sense, all's fair if you can find some other way of working out that area. If the function is positive, greater than or equal to 0, then the integral really does just mean an area. So although this function is definitely not a power of x, you can integrate it by working out the areas of these triangles. There's a sort of switch that you're expected to be able to do between area under the curve for a positive function versus the integral. If they show you this integral and the function is weird, like it's not a power of x or some combination of powers of x, then presumably you're going to switch to thinking about areas instead. Right. Can you integrate x factorial? I don't think I've even got a definition of x factorial when x is not a whole number. Except I do actually, but I'm pretending not to know about gamma functions because I don't want to talk about gamma functions right now. It's a tough job, isn't it? Area below the x-axis is negative. That's one way of thinking about it. Some people say that all areas have to be positive. So the signed area is negative for this bit down here. But the actual area is a positive number. Put a minus sign on it. I think my personal opinion is that I quite like signed area. I think signed area is telling me something. It's my preferred quantity. But lots of TMUA questions ask for area, which has to be positive. Yes, okay. Ooh, arc sign, except the triangle's below as well. Right, okay. We're working our way through revision notes. It's already 5:30, so I should maybe speed up a little bit. Just a little bit. There's the trapezium rule. You are, for purposes of TMUA, supposed to know this rule, which is a bit complicated, isn't it? But I reckon you can learn it. The idea is that you split up that area, if we care about finding areas, to use trapeziums. I think that often when this is taught, people are probably only talking about positive functions, like f greater than 0. It's just easier if you have to teach people about the trapezium rule to just teach people about the trapezium rule for positive functions, in which case the integral is an area and you can talk about the area. I have tried to write my revision notes doing it properly, even though that's harder for both me and for you. I have tried to write my revision notes so that it includes the case where f is negative, just in case. You know, it'd be tricky if it came up in something, right? But just in case, I thought I should write this so that you would get stuff that works even if the function is negative. So these rules work even if the function is negative, in which case the integral is not telling you an area, it is telling you negative an area. So, be really careful with overestimate and underestimate. Chat wants to know about the integral of sine x, not on TMUA specification. If you know it as a fact, no one can take that away from you. Enjoy your fact. It's a good fact. And not going on screen because I don't want to panic anyone, but some of you know facts about sine as well. It's good. Okay, right. I think we've had a look through some of these bits. Use of second derivatives here. Let's just draw a picture because I've decided this should have a picture. So split really quickly. There's this case where f prime prime of x is positive. We didn't talk about this in the differentiation session, but the first derivative tells you about the gradient at any point. It's a function of x. And if it's positive, the function's increasing. If it's negative, the function's decreasing. So there's this sort of graph that you could consider where the second derivative is positive. What's that? That's the derivative of the first derivative, which tells you not that the function is increasing, it tells you that the gradient is increasing. So look, that's what's going on here, right? It's over here, the gradient is negative. Over here, it's negative, but less so. It's increased. Over here, it's actually 0, and then it keeps increasing. The gradient is now positive, and now the gradient is very positive. The gradient is increasing, and that captures this idea that the function is convex. It's curving upwards. We don't need to do, okay. Yeah. And someone in chat has pointed out, let's put chat on screen. Go on, they're being entertaining. Yeah, something like that's the function that you look at when you're looking at maxima and minima. You look at the second derivative. Although for maxima and minima, you just evaluate it at a point. So if IFAP is correct, that's you've seen two derivatives before. And then I do have a bullet point that says two derivatives equals 0. It's a complicated way of saying a straight line. Yeah, I agree. I thought I'd list it like that to match the other cases. Good fun. Pecky, people do use third derivatives. The third derivative tells you how the second derivative is changing. So gosh, if you've got a function that looks like this in one place and looks like that in another place and changes, then you might be interested in the third derivative to talk about how the curvature of the graph is changing. You know, how do we decide where to put the points? For the trapezium rule, you equally space the points between your endpoints. The rule is that you take n strips, which will require n plus 1 points. The first one or the 0th one, depending on how you count. But let's say the 0th one is A, the nth one is B. There are n plus 1 of them. Oh gosh, so many out by 1 errors you could make here. But they go from A to B. There are n plus 1 of them overall. N minus 1 point in between, equally spaced. I've now said that too many times. Right, good. Okay. Quite a lot of different things we need to know, but not that many functions we're supposed to be able to integrate. It's feeling a lot like chat knows how to integrate things like 1 over x, and chat is worried about problems with 1 over x squared, which I think we should not worry too much about. And chat is interested in integrating sine and cos. Yeah, okay, you know it's called torsion. Fine. Okay. What do I want to do? I want to look at some revision problems. So let's have a quick look at that. They are over here. We'll do a few of these, I think. I've got a choice of 13 of these, and I think I'll switch on a poll for people to vote. I hope I've done that right. Yeah, I think I've done that right. For this, there are several questions. Maybe you've tried some of them before, because we put this up last Friday. Oops, 6 days ago. Should have been 7. It's going to be 6 again for the next one. And some of them are harder than others. In particular, question 4 is pretty tough. People are voting for 2 and 3 though, which are on screen. Let me scroll a little bit. 5 is new for this year. I thought I'd write this question about contiguous ranges, which is a phrase that's in the specification, and something funny about graph transformations. And then fundamental theorem of calculus, which you can do stuff with. A slightly silly question 9 about integration where the limits are the same. Trapezium rule. Just come up with 2 questions. 1 where it's an overestimate, 1 where it's an underestimate. Surprise. And then 12 differential equations are on the specification. So I've added a differential equation to the revision questions here, just in case you want to practice that sort of thing. I've tried to give like an extra bit of information that I want the one where y is roughly 3. I get to give you an extra bit of information because when you do that indefinite integral, you have a constant plus c. And I get to tell you another fact that might help you to work out what the plus c is in order to satisfy this other interesting constraint. So people are voting for 4, 12, 5 and 2. I've got 12 on the screen, so let me just talk about this. Your job is to find a function y, function of x, such that the derivative dy dx is 1 over x squared. So if you differentiate it, you get x to the minus 2. And maybe if you know that integration and differentiation are kind of opposites of each other, not quite, we can make them more precise, but you know, if you know that the derivative of an integral is the function itself, which is the fundamental theorem of calculus. Not that I knew that when I was in school, but you know, it's called the fundamental theorem of calculus apparently. Then maybe you can find a function, or think of a function, or remember a rule about functions to integrate x to the minus 2. Don't forget the plus c. Right, good. But question 4 is winning the vote. Let me put the vote on screen so it's recorded for all time. Question 4 is winning the vote, and it's not close. 12 is there as well. 2 and 3 are in the running. Let's remember that. But it looks like the first few questions. 4 is arguably, oh, I know it is. It's one of mine. Let me explain. So question 4 is a question about integrating 1 over x, which is like precisely the thing that you can't do using the TMUA specification, because it's got that term in it. Go and check if you like that says n is not equal to minus 1, which oops, let's see if we can reason about it anyway. Something I'm hoping that you either know or that you can intuit is what happens to a region, an area, if you stretch it. So here I've got 1 and 10. My idea here to relate together I1 and I2. So instead of integral from 1 to 10, to think about integral from 10 to 100, those x values from 10 to 100 are 10 times as large. So my idea is maybe to stretch this of 10, question mark, I don't know if you know what happens when you to an area when you stretch by a factor, but it goes up by that factor. So if I do that, and I get this, I'm going to put it over here. Although 100 should really be quite a lot larger, shouldn't it? So this is a larger area. It's 10 times I1. Because I've taken that first integral, that first area, and I have stretched everything by a factor of 10. There's a problem, which is that that's not the integral of 1 over x, because this is no longer 1 over x. It was 1 over x over here, but then I stretched it. There is this really nice rule, though, about how stretches work. So graph transformations, which I think we'll talk about next week on the graphs worksheet, which you haven't seen yet because I haven't published it yet. Oops. But there's this really nice thing that if we want to get back to 1 over x, we could maybe stretch parallel to the y-axis as well. So what is this? I've stretched by a factor of x parallel to x-axis. So this is the graph y equals 1 over x over 10. This rule for how do you write down the graph after you've done a stretch like this? If you've stretched parallel to the x-axis by some scale factor a, then you have the graph of f of ax. Oh, sorry, let's get this right. F of x over a. Oh, that's annoying. Which, if you simplify it for this particular function, the 1 over x function is 10 over x. So maybe it's not surprising that we've got a larger area because, well, we're integrating a larger function. Charlie wants to know about Gabriel's horn. Fun. There's a roughly 3. Question about 12. Yeah, okay. Okay, so this is a different curve, but we can fix that. I'm going to say squash. I guess I also mean stretch by a factor of 1/10 parallel to the y-axis. So I've got this stretch which moves the range under consideration between I1 and I2, and then I can think about doing a squash. I'm going to zoom out a little bit to show you this picture. Missed that. Okay, still not good. There we go. We can squash it. If we squash it by a factor of 1/10, then we get back to 1 over x. And our integral, when you squash, will go down by a factor of 10. So the area is now equal to I1. So it's been stretched out like toffee, but also squashed in the same amount of toffee. You stretch it out, but it gets thinner, which would be like a stretch and a squash at the same time to conserve the total area. Yes, the combination of these stretches would be, yeah, careful. So chat has made the same mistake as me. Has it? No, chat's made the opposite. Chat's done the correct one. Sorry, chat. Anonymous person. 1/10 of f of x over 10. After doing the stretch parallel to the x-axis and then the stretch parallel to the y-axis, which for this particular function cancels out. That's the nice thing about 1 over x. And this thing cancels out. Which then, if we're doing question 4, having done these stretches, so stretching out the area and it's squashing it down, so that's the same area I started with. It got 10 times wider, but 10 times shorter. So overall, every little piece of this area, if you like, if you want to imagine it made of little parcels, has got wider, but then flatter. So it's still got the same area. So all of the little squares, if you like, if you do grid squares for your areas, whatever, all of those have been stretched up and then squashed. Can we do this without having to think of the graph? There is a way to do integration by substitution. Integration by substitution is not on the TMUA specification, so I'm trying not to talk about it because I think half of the people will have seen it and half of you won't. Yeah, you should not try to integrate functions that blow up. If your function is not defined at some point in the range, then I claim the integral is not defined. Now, you might have some expression that you would write down for it, but I think a function has to be defined to be integrated. Why are we multiplying by 1/10 if it's a vertical? Well, so at the moment it's 10 over x, and I'm trying to get it back down to 1 over x. What should I say for that? Should I say stretch by a factor of 1/10? Would that be less confusing? And so I'm stretching it out this way. All the values are too high. So any point on the curve, I stretched it this way, and that's kind of a mistake, and then I'm trying to stretch it down so it ends up back on the same curve. Because in the question at the top, I'm trying to talk about 1 over x again. Vertical squash, says Erica. Yeah, maybe squash and stretch mean opposite things. I should watch out for this. Hopefully the sequence of what I'm describing is we can argue about where the factors of 10 go, but it turns out that you stretch and then squash. Anyway, for the purposes of this question, this shows that those integrals are the same, and they have contiguous ranges. This one goes from 1 to 10, and then that one goes from 10 to 100. So if you went from 1 to 100, you would get both of them. And you could do this again. To go from 100 to 1,000 would be, for the same reasons, stretch and squash, would be the same area again, just thinner. And the graph of 1 over x keeps going forever, getting, smaller and smaller values, but we can find, using this method, areas that are equal, more and more of them, areas that are equal that have been squashed and stretched out. So you have to wait a long time. Something to do with 10, 100, 1,000. That's the kind of scale for how long you have to wait to see each of these bits of area. You have to wait longer and longer, kind of exponentially long. But eventually you will see another chunk of area coming past, very flat and very wide, which means if you keep going, you can get as much area as you like. So this is a proof that the area under 1 over x is unbounded, even though the function is going to 0. It's weird, and that's one of the reasons that you don't learn about it at the same time as all of the other powers of x. Is this a revision question? Not really, right? This is a graphs transformation question, but I've included because I think it's fun. Yeah, okay. Multiplication with water. Oh, that sounds fun. I do like fluid dynamics. Stickers. Yeah, so this is a special property of the 1 over x graph, that you can do this pair of translations, stretch and squash, and get back to the same place, same function. And we'll do it one more time, just in slow motion over here. It's 1/10 of 1 over x over 10, and the 10s cancel, so you get 1 over x. You get the same graph. Amazing. Yeah. So you can go on to do all sorts of fun things with this. Chat is suggesting some of them. Right, okay. But you didn't want that. You wanted questions 1 and 2 and 3. Was it 1 and 2? 12 and 2 and 3. Let's do 2 and 3 while we're here. It's 10 to 6. We should probably do some TMUA questions at some point. But I'm having fun. So 2 tests different methods. Although we only really have one method. So we're going to use that one a lot. A method for stuff like this is an indefinite integral, just has to be to try and convert this into powers, separate powers that we can integrate separately. So here I've taken the fact that this is 2 fractions added together, x over x cubed plus 3 over x cubed. And then you can integrate this by integrating each term separately. The game here with this question is that I have to try and find ways to disguise powers of x, and then your job when you're doing this question is to try and work out that they are just powers of x. So you'll be fine from here, right, because you know how to integrate powers of x. And then this one, maybe, I don't know if this got anyone, but this is another way of disguising a power of x, because on TMUA the only thing you can integrate is powers of x, and then x squared plus 1 cubed. Maybe you want to try something clever involving a substitution if you know about those, but I don't think you really should. I think you should just multiply it out. It's not that many terms, right? And now it's just powers of x, so you should probably just integrate them one at a time. Cubing is not too bad. What's the biggest binomial expansion power they can ask on TMUA? Technically any of them, right? You know the binomial expansion with n. Like, there's nothing wrong with putting 30 in here. We had a question on the algebra worksheet where I asked people a question about, what was it? Was it like x plus 2 to the power of 300 or something? Right, but there the joke was that you should not actually expand all of the terms. I think that was the very first question sheet. Like 2026, welcome to the Mathematicians Test livestream. Would you like to multiply out x plus 2 to the power of 300? Don't know. What if in our first problem we went to x, not 1? In our first problem? Oh, are they trying to get me to integrate 1 over x? Possibly they're trying to get. Is there a name for functions? Says chat. Oh, let's get it on screen. Is there a name for functions where you can do the same kind of transformation and get the same graph? Oh, we don't have time. But yes, this is definitely a thing. If you have some transformation and you have something that is unaffected by your transformation, that is very much a thing. And in general, your transformations will mix things. But occasionally you find an object that is stationary, the eye of the storm, where everything else is being transformed, but that thing stays still. It's a whole thing. Look up fixed point. But if you just look up the phrase fixed point, you're going to find the most mundane version of it first. Yeah, okay. Right, 12. I wrote 12 for this year. It's kind of a new one. I haven't really tested it on as many people as some of the other questions. Yeah, we do this for a few years, but there's always room for new questions, right? And I've read in chat. Let's have a chat back. You're not covering up any questions, chat. Just happy there. I've read in chat somebody being unhappy with me about. Let's see. So the solution to differential equations like this, where you have the y by dx on the left and you have a function of x on the right, for TMUA that is, all of the ones we are going to work with, is this, which it really is a power of x inside there. I'm going to write square brackets. I'm going to write this plus a constant. I've divided by my new power, which is -1. I drew some weird symbols while I was thinking about it, but I've divided by -1. After a while, I've decided to just write a minus sign for the dividing by new power -1. And my intention with this was that you would say we want y roughly equal to 3 for large x. Large x is precisely where this 1 over x doesn't really matter. 1 over x will be roughly 0. So take c equals 3. I do accept that because of the approximately equal to, you could be justified in taking c to be some other number that's kind of close to 3-ish, and then saying, well, I did this, it's approximate. Not my intention. I think I need to find a way to say, I think it's going to have to be horizontal asymptote, isn't it? That's going to be no fun. Horizontal asymptote next year. Okay. Approximately equal for large, but yeah, I'm trying to do a limit. I can't say limits because we don't have any limits. We don't have the concept of a limit. Yeah. So a hard question, Anonymous, is if you have something, can you, if you want to find this, can you find it? Yeah, revision question 6. Thanks for asking. You've said please. Let's have a look. Okay, I've got to rephrase this like approximately equal to 3 business. I just wanted to give you a clue for the constant. How about if you put pi, just give yourself a tick, and then everyone's happy. Right, okay. So you should definitely not do this integral. If you do all of maths A level and all of further maths A level, then at some point I think you will learn how to do this integral. But the question says without calculating any of these integrals. So given that it has got a name, it's called I3. I think I'd already used I1 and I2. Yes, this is integral 3. Okay, chat is going to tell me that, yay. So the question wants us to find an expression for this. I'm writing very small. Let me zoom in. There we go. From question 2, where we had these things in disguise, one of the things I want you to take away from that is that you should always try and simplify things before integrating them. Now, for this question, we're not actually going to integrate because it says not to. But still want to simplify anyway. And in general, when you have a fraction like this, you know a way to simplify these. This is polynomial divided by another polynomial. If the polynomial in the numerator has a large degree, at least as large as the denominator, then you can do a little bit of polynomial division. You can simplify things. I'm making that sound harder than it actually is. The thing I'm actually suggesting, it is a hidden quadratic in terms of this, I suppose, is that we write it like this. Oh, I've messed that up already. It's not that would just be this. So this x squared is a bit like x squared plus 1. I wish it said x squared plus 1 up here. If it said x squared plus 1, I'd be so happy because then the integral would just be 1, right? Integrated from 1 to 3, so 2, final answer. It's not that, but I can almost get that. Here's a true fact. Right? Like I can add 1 and subtract 1 because I'm so desperately want to see x squared plus 1. And then if you remember in question 2, we split a fraction into 2 terms. That's what I want to do here. I want to split this one, the one that I can do. Okay, there's a minus sign. But this bit is I3. No, it's the thing that you integrate for I3. So I have an integral that I'm willing to do and an integral that I've been told not to do, but I recognise. So this is the integral of 1 from 1 to 3 minus I3. I think that first thing is 2. Right? They compare it to a thing that I've got, or compare it to an integral that I'm willing to do. And I'm pretty lazy, so I'm only willing to do integrals like that right now. Yes, okay. Was it secretly quadratic? Yes, okay. Yeah. If you have the integral of a constant, so integral of a constant from a to b, this is going to be a pretty expression, isn't it? It's got a, b, c, d in it, and an x. The integral of a constant is c times x, a to b, because a constant is secretly c times x to the 0. X to the 0 is 1. So you add 1 to the power, and you divide by 1. You divide by the new power. Nobody actually thinks about it like that, do they? They just memorise separately. The integral of a constant is c times x. And then you plug that in, and you get c times b minus a, which is another way of saying that if you have a flat line function, the area underneath is the product of b minus a and c, the constant. If the function is positive, otherwise you get a negative number, and that's negative the area. Right, goodo. What are we doing? Oh, we've got another one because it also says x to the 4, and then it is time to pause, isn't it? But maybe you've seen where this is going. Now I've shown you this one, person who requested question 6. We should simplify first. And this is crying out to be simplified, right? Like it looks like it's not quite x squared, because that's not quite x squared times the numerator. Now, I never really know how much people have learned about polynomial division. I also don't really care how much people have learned about polynomial division, really, because you can get away with quite a lot, look. So I'm sort of willing it into existence. I want to see plus x squared, because I can simplify that term, right? I wish it said x to the 4 plus x squared times the things down here. And I wish it said that, because then it would just be x squared. And okay, consequences, I've got this other term. It wasn't really just these two terms, it's got this thing in here. But that's just this. So this is the integral of x squared. I should put my limits on, because it was definite integration in the way. So it's an integral that I'm willing to do, and an integral I've seen before. So it's the same sort of joke again. Is it a joke? I don't know. Deadly serious. Okay. We happy? A little bit. What is going on with that username? Sorry, chat has gone a bit Monoid is a monoid in the category of endofer. Great. Okay, some category theory. What is a large number? Yeah, okay, fine. I think I said large number at some point. Rephrase my question to not say large and not say this. Oh, you're not going to like my solutions. I say large number all the time. I just kind of mean keep going until the following is true. It'll happen eventually. Right, okay. Quick pause. It's 6 o'clock. If you've been looking at a screen for the last hour, remember to occasionally look away from the screen. Remember to blink. I'm going to drink some water. There's going to be a vote that's happening at the same time. Simultaneous activity. We've got questions like this. We've got things with integrals in. And we are going to do a quick vote for which question we're going to do next. So let's switch on the vote. Let's put it on screen as well. I'm going to drink some water. I've done an extraordinary amount of talking today. Somebody showed me on their phone, so I was talking to a summer school, and I've been talking to the summer school for quite some time. I talk a lot. I should talk probably less, especially on summer schools. And someone showed me on their phone that they got the notification for this live stream, and it was the kind of horror of realizing that not only had I been talking a lot, but I was about to go live and talk to a camera for a further 2 hours. Here we go. They're currently voting. They're currently voting for the one that's on screen, which is pretty exciting, but also for one that's down a couple of pages. So I'm just going to scroll a little bit. I think chat is going to hide some of this question text, but here's one about the fundamental theorem of calculus, where a student is doing a calculation, and the student, spoilers, does not get the right answer. We must mark their work, it says in this question, more or less. Where's the error? One of the options is the student's correct, which is not the case. I have seen a past question where a student has done some work and it's just correct. And I've also seen a question where the student's done some work and they've just made a really stupid error at one point. And the question is, can you find the stupid error? I've picked this one for the live stream, though, looking back up a little bit, because the student has made an interesting mistake. And I think it's worth us looking at if people vote for it. It's coming nowhere in the vote at the moment. That's fine. We don't have to. This one is super hard. Question 3 is coming second in the vote at the moment. It has got lots of absolute value signs. I see you voting for it. There we go. Oh no, you voted for the other one. As we went past it. Okay. They're currently in order. Let's see if I can draw attention to other ones. Here's this question with triangles that I was talking about, where you'll need to remember that the integral is something to do with area for a positive function. And then it becomes easier because area of a triangle is much easier to think about than integral of a triangle. I would much rather find the area than find the integral, even though those are the same thing. It's nice, isn't it, when one thing's easy, one thing's difficult, and they're the same. Right, okay. Functions. I put this on the integration sheet because it does ask an integral. So, there's some practice down there. Although, spoilers, it's triangles again. So this was doing well in the vote to start off with, but other people have voted, and now everything is on 56%. So I don't know what to think. I'll just keep talking, I guess. There's some integration, but it's triangles when all the dust settles. The question here is really about the functions. Got to look at functions at some point. And then finally, a medium standard question, just hiding chat for a second so you can see the function. A medium standard question about finding an area between a curve and the x-axis. The line y equals 0, otherwise known as the x-axis. The function has got absolute value in it, so we'll be a bit careful, but I don't think this will look too out of place on an A-level paper, maybe with a bit of help. I don't know, you'll be alright. Everything's now on exactly 60%, which is exciting. Everything? Not quite everything. 1, 4, and 5. I wouldn't mind a tie. I'm going to get scrolling. And I'm going to keep blinking. Scrolling past all the hints as well. And we released this question sheet in advance with hints and with solutions. So in some sense, if you're fed up of me scrolling up and down through a PDF and you just want to get some answers, then This is the only YouTube live stream that periodically reminds you that you don't have to watch the live stream. You can get answers in a different format. Although apparently I've screwed up the formatting on. I've messed up the formatting on the page, so that's irritating. I should go and fix that after the show. I wonder how bad it is. Right, question 1 is winning. Let's have a quick look. And I've scrolled all the way back up. So let's pause. 1-4. I might let them keep voting. I'll leave the poll on. Chat saying anything at the same time? What's chat saying? James, you better not be. Right, no, hang on. Beth's getting involved. Someone's asked about Chill Maths. Chill Maths is on a unpredictable break due to me doing things on the weekends. I think Chill Maths might be back this weekend. Chill Maths is a separate YouTube thing that I'm involved in. Not a YouTube thing. Chill Maths is a separate live stream thing that I'm involved in that is not this one. But occasionally people find me in this live stream to ask me when the next one of Chill Maths is. I think this weekend. I've been busy. Summer's cool. Good. Now I've mentioned Chill Maths and people are like, oh, there's Mary and Ginger. Hello. Okay. Yeah. Okay. Beth's moderating chat. And Beth's doing a great job. Good. Veering off from not doing the self-promotion. People can find Chill Maths if they want to find Chill Maths. It's just not helpful for TMUA. So my main mission here is to be helpful for TMUA right now. Right, okay. So we've got a function, and we've got some horrible integrals of the function. I mean, yuck, right? Like, it's even worse than the one I showed you as the warm-up problem going on. We've got a function that's being squared. Ooh, has that crashed? No, that's back. YouTube just gave me such a scary, like, everything switched off. I think that shouldn't scare me that much. Worst case scenario, I'm just talking to myself. Right, okay. We're given a function that's been squared and then integrated. We're not told what the function is. We should not try and solve for the function, by the way. I've seen a few questions like this where there's an unknown function. If you can quickly think of an example, that can be helpful. But I've seen a few, and I've never been able to think of a function quickly that does this. I mean, look at that equation, right? Just thinking about a function that works is, I think, harder than doing the question. So let's not. I think extension activity is to think of a function that does this. Hard. Right, what are we doing? We've got to make a statement about the following claims. There are only 2 of them. Claim 1, claim I, the function is negative for some x or equal to 0, less than or equal to 0 in claim I, let's be careful, for some x between 1 and 3. And for me, the question is really, how on earth am I going to say anything about the values of the function? So values of function between 1 and 3. So this is like one thing that's in my mind because it says that over there. There's like integral of f of x squared, and there is like an integral from 0 to 3 of f of x dx, and an integral from 0 to 1 of off the screen, an integral from 0 to 1 of f of x dx. These are kind of the things in the question. And then, like in red string, we've got to connect up all of these things, right? So these things are related because they appear together in an equation on the board. And then these things, so the values of the function, they'd be related to the integral from 1 to 3. That would have something to do, when I say values of the function, that's got something to do with the area, provided that you integrate. And so maybe this integral tells me something about an area where the values are positive. And then the big connection for me was when I realized that this integral and this integral and this integral are very closely related. what would the rule be? Is this thing about contiguous ranges. The integral from a to b plus the integral from b to c. You pick up where you left off, you get the integral from a to c. You can stick the ranges together. If you want a mental image, you can imagine the trapezium rule, right? You can imagine a stack of trapeziums over here and a stack of trapeziums over there. If you have contiguous ranges, you're just joining together all the trapeziums. So breakthrough for me is realizing these things are connected, which means it's all connected. Everything this question is asking me is there. Right, okay, what do I need to do? What do I need to do? None of this. This is all very, very silly. What I need to do is I need to write down a true statement. What's my true statement going to be? It's going to be something to do with the integral from 1 to 3. How do I get the integral from 1 to 3? Well, this thing, which is something to do with the values, is the integral, if I use the other two, the ones that appear in the question, it is the integral of 0 to 3 f of x dx minus, I don't want the bit from 0 to 1. Again, that's contiguous ranges. If that is a leap of logic for you, then try moving the right-hand term, the last one, onto the left, and realize they would stick together. They would glue together like a Lego bricks or something, joining together 0 to 1 and then 1 to 3. Snap, 0 to 3. I mean, I've just moved that thing over there. I guess I've got this like confidence or fluency that this will just work out. Like I'm subtracting that bit of the integral from that range 0 to 3. So for me, they're kind of like the ranges are being the things that are being subtracted or added. You can join them together like this. Anyway, these things are relevant because they're in the question. This is minus the integral from 0 to 3 of f of x squared. And what do I want to say? I want to comment on whether these values are negative. So I'm thinking about negative numbers, and then you can't really miss it that there is a minus sign over here, and these squares are positive. So this is an area. Once you've integrated, and it's got a minus sign at the front, so this will be negative or 0. I've pointed at loads of random stuff now. It's turning into one of my red line diagrams again. Question mark then. Is it true that the values of the function, at least one of these values, some value of x, is negative? I think it has to be, because the integral is negative. Any proof by contradiction, right? If the function were positive or 0 throughout that region, then when you integrate it, you would get an area. Or maybe you get 0 if your function is 0 throughout. But the only way to get a negative number is if you have a negative value at least somewhere. Good times. Right. Last part once again. Okay. Thank you. I don't know how much stream lag there is, so I'm going to explain this bit once again. So slow motion replay, not even slow motion, just do it again but better. Me, I'm going to do it better but better. Do it again. I'm going to do it again but better. So f of x squared, I'm thinking about negative and positive because the question says f less than or equal to 0. So I'm thinking about negative and positive, and I know that all squares are positive or 0. So we're integrating something that is greater than or equal to 0. F might be doing anything. It's gone off the bottom of the screen. But f squared is greater than or equal to 0, which means that when you integrate, you get an area between 0 and 3, apparently. You get some area. Areas are positive, which is a long-winded way of me saying that if you integrate a positive function, you get a positive answer. Kind of sounds obvious, but again, we don't really have a definition of integration, so there's no way for me to justify that claim. It's very irritating. Anyway, never mind. There's a big minus sign at the front, so this is less than or equal to 0. And then last part is we're asked, are these values negative over here? So it's kind of irrelevant right now that we're integrating from 1 to 3. Like all we've got really is that we've got this. I shouldn't say irrelevant. Everything is relevant all of the time, but you know, this thing is negative. If you integrate this function, you get a negative number. So it cannot be the case that this function is like happily positive values all over the place, because then when you integrate it, you would get a positive number for the area underneath the curve. If it's positive everywhere, that's ridiculous then. But if this thing is going to be negative, then the function must be 0 or negative somewhere. Probably lots of places. Probably it's something like this. where it's got this big negative contribution so that the integral overall can be negative. Good. Okay. So I think that's kind of, you sort of follow the breadcrumbs, right? They've asked us about the range 1 to 3. Okay, check my solutions because I've become very scared. Most of the things you're asked to show. Yeah, okay, so this is necessarily true. Let's put the word necessarily in bold. But because it is true, there's not really much to think about there. It just is a true fact. The word necessarily here is highlighting the idea that if it depends, if it's true for some functions and false for some functions, they would like you to say no to this claim. Necessarily true would be it has to follow for all of the functions. If I choose a student at random, are they necessarily British? It would have to be the case that they're all British, and I don't think that's true. Necessarily being this kind of strong everyone. I don't know why I picked British students as a thing to single out as my example of a thing that might or might not be true. I don't know. 2, right. Beth says we didn't learn what an integral was until the end of first year maths at university. So yeah, I'm not trying to be rude when I say you don't know how to integrate. You don't know what integration is. You don't know what integration is. But you find that relaxing, right? Like in general, someone shows you a function and says, "What's the integral of this function?" Right? Something to do with area. But what's area? That is a dangerous thing to say to a room full of people, isn't it? Oh, yeah. Oh, chat. I don't really believe in area. I only believe in integrals. I think this is probably something that's wrong with me. I think that integrals are real, and area is something that we have made up that's based on integration. Oh no, which is why I don't find it very convincing to say that the integral is an area. For me, the area is an integral. This is a bit of an unhelpful opinion to have right now. I can feel the room turning against me. I've got to talk about claim 2, haven't I? Claim 2 is about these integrals. We just had these integrals. They were on the red chart board, weren't they? The integral from 0 to 3 and 0 to 1. That's just what you get. Well, no, let's read it off the question. In the question, we can see one of those integrals, and something's been added to it. That first term, it's been added to it, and we've got the other one. What are we adding? We're adding a positive quantity, right? Because f squared is positive and it's been integrated. So when you integrate a positive thing, you get a positive thing. So the thing on the right-hand side must be larger, right? It must be larger than integral from 0 to 3. It's a bit weird that it's larger because the integration is over a smaller range, but integration is weird like that. It involves negative numbers. Don't stress. So I think 2 is true as well, because the difference between those integrals is that positive quantity about f squared being integrated from 0 to 3. So I think they're both true, which is option D, both of them, necessarily true. Now this question is really about inequalities. Nothing actually gets integrated in your rough work while you're doing this question. There's maybe a thing there about contiguous ranges, to say what's the link between 0 and 1, 1 and 3 versus 0 and 3. Stick them together. But you don't actually have to do any integration to this question. Do they teach this firmly now at A levels, or does it vary? The thing that Beth and I are joking about, this thing that you learn at university, is definitely not going to turn up in A level, because it's surprisingly difficult to explain what integration should be in general. Like really in general. At A level, people learn how to integrate certain functions. There's certain things that you learn what the integral is. And that lets you do like fun stuff, right? So for one of your functions that you know how to integrate, you can do things like find this area, stopping here. You can integrate the function, but you can do like typical stuff, find this area underneath this function, There's loads of games to play over there. There's even ones that are kind of surprising. Like, I think depending on which bits available you do, you learn that this function, which is 1 over 1 plus x squared, has an integral that involves pi. So you get pi 3.1455, turning out of this expression, which has got no circles in it. So sort of pi turning up in this like non-circular situation. Different sort of geometry, isn't it? It's just good fun. And then at university, you find out how to do this in general, even when it's not something cute like pi as the answer, which is good. Right, okay, am I doing an advert for university? I think I might be. I've done one TMUA question. Yeah. Right, okay. Right, I'm not going to rise to the question. The question in chat about my opinions about area, I've got to ignore them because I've got to talk about fundamental theorem of calculus instead. Gosh, I love integration. We do go a bit off topic sometimes, don't we, chat? Just a little bit sometimes. Okay, what else did they vote for? They voted for question 2. I'm going to scroll. Question 2 is tool, and I think for this one I'm not going to write stuff. That's not the button I meant to press. I meant to press that one. Hide that. Show that. Big tool stack. Last line. Let's see if I can get that. Yep, that's good enough. There we go. We've got the whole thing on screen. Absolutely all of it. Good times. Here is a question with a student doing a calculation. And spoiler alert, the student's maths is not correct. They're trying to use the fundamental theorem of calculus, which they've got a statement of at the top. And there are several lines of work. All of the boring stuff is correct. Like the student has done some contiguous range trick at the top there. Worth looking at. That's that line that's labelled I, step 1, is it's true, and it's maybe a good trick that you could use. It's a bit like the thing I said right at the start about indefinite integration and definite integration with an x with a variables top. It kind of works. Or you could think of it as a contiguous range fact, if you like. You could. There's nothing special about the number 0. So just looking at this like line 1, there's nothing special about the number 0. You could put anything you like there. Right, and then so that line's fine, which is good. And then in line 2, they're using fundamental theorem of calculus. And somewhere things go wrong because the correct answer at the end is not 3x squared. Fun activity, right? Is that you could try doing this question yourself. You could have a go at this. It's not too hard to literally don't think about fundamental theorem of calculus, just do the integral and then take the derivative. So first off, you integrate t squared. If you do that, you will find slightly different answer out the end. It's not 3x squared. And one option is, once you've got your kind of correct answer at the bottom, is you go through and check all of their lines, right? You have to integrate t squared quite a lot of times if you want to check every single thing that's on the page. But that's one option available to you. Or you could try and look for the line where they have misused a theorem from maths. Has chat got any ideas? Chat is currently being chat. People voted for this question. There is a lot of stuff on screen here. I think it is the tallest question we've looked at on the live stream this year. But it's just a format of question that I've seen a few times on TMUA, where you're presented with a lot of stuff, and your task is to read it looking for mistakes. Yeah, Pecky has got a good idea in chat. Nice. By the way, general advice for reading stuff like this, where you're looking for a mistake, is to work line by line from the top, but occasionally glance back to the top. There's usually important information at the top. For example, here at the top we can find the fundamental theorem of calculus, and we can find a statement of what the student is trying to do. So occasionally looking back up to refresh your memory of what you're doing as you go through. It's also quite good when you're like solving a tricky problem and you're likely to forget what you're doing. We've seen a few times on here that there's sometimes like extra terms and conditions, like the thing is a whole number that's greater than 2, that just it's only relevant near the end. So things going on. Yeah, Anonymous has got a suggestion for how to improve this, or what they should have done instead. And it's step 3 that I'm suspicious of. Rachel's suspicious about step 4. Let me have a quick think. Oh, I think differentiating each term would be okay. They've definitely got the wrong answer by now, but in step 4, differentiating each term with the minus sign in between, I'm sort of okay with that. If the derivative of the first integral really was 4x squared and the derivative of the second integral really was x squared, then the derivative of that combination, f of x minus g of x or something. I think I'm muddying the water by bringing in f and g, but like 2 functions, the derivative of those, I think it'd be okay. Okay, but edit, never mind, that does work. Okay. And then step 5 is just them tidying things up. I don't really know how you could possibly pick step 5 as being the one with the mistake. I guess if you kind of strongly believe that 4 minus 1 is not equal to 3. Yeah, no, probably nobody believes that. I don't have the statistics for who picked which, where is the mistake, right? I kind of want to see the heat map, like, where is people's suspicion focus, like unsuspicious, suspicious, and then back down to not suspicious again, line by line. That'd be a fun chart. I've seen, I mentioned this a few times, I think if you show mathematicians a proof with a mistake in it while they're wearing eye tracking software, I should be doing it now, shouldn't I, for the stream? Eye tracking software, you can see where they look. And you get these fun heat maps where there is a big blob on the mistake, but there's also lots of like glancing back up to check the terms and conditions at the top of the statement. Like, here, what are you trying to do, and what's the fundamental theorem of calculus? What does the fundamental theorem of calculus actually say? So I think you would see, if you showed just a mathematician who's looking for the mistake, I think you would see scanning along the lines and going back up and down. But you could see quite a lot on step 3, where there is a 2x at the top of the integral, the upper limit. That's the integral from 0 to 2x. And I think you would see a heat map blob inside the fundamental theorem of calculus at the top, where it is a 0 to x, because those things are different. And the student has not used the fundamental theorem of calculus there. They've used their own special version, where you replace that upper limit with whatever you like. Sorry, that's made me laugh. Chain rule! Not everybody knows the chain rule, but if you know the chain rule, you know that you get problems if you have a function of a function, so f of g of x, then the derivative of that is not just f prime of g of x. People who don't know the phrase chain rule and don't know why that's funny to me also know that you shouldn't use fundamental theorem of calculus with 2x there, because 2x is changing in a different way from how x is changing. It changes twice as fast as you change x. And they've tried to fix it by plugging in 2x as the thing that's being squared, but I'm afraid this is not a general rule. If you like, in the fundamental theorem of calculus, one way to see this, because I kind of feel for the student, right? Like they've done their best. The top limit x should be the same. If I was trying to help the student, I'd point out that in the fundamental theorem of calculus, and it is hard, but in the fundamental theorem of calculus, this statement, this x, they've correctly spotted that this x is the same as this x, but you take the upper limit and you put it here. But unfortunately, this x is also the same. These must match. And the thing that they are trying to achieve is d by dx with 2x up here, so they don't match. So you're not allowed to just take the upper limit and plug it in. You need these things to match. And it's confusing perhaps because there's also these going on and they don't match. They don't match. Well, they match each other, but they don't match those ones, and that's all right. Those don't have to be x. There's just a different letter. It's a dummy variable. Yeah, so, it's fine. Okay. So, moral of the story: apply theorems as stated, even if you want to make a small tweak to a theorem. I think in the solutions document, which is also on the MAT Live website, I've written up, because I couldn't resist it, there is a better version of the fundamental theorem of calculus. Girls just want to have fundamental theorems of calculus, and so do I. I couldn't resist showing you a better version that includes terms where you can have whatever you like in the limits. Here they depend on x, both of them. There's a general rule for that. If you want to see it, I don't think you're going to need it anytime soon, but if you want to see it, how do you use the chain rule to fix this problem? I put that in the extension bit of the solution to this question, or the solution bit of the worksheet. I've lost the train of that sentence. I've put that on the website somewhere. See if you can find it. What are we doing? Yeah, right, okay. There was a request for triangles, and also I saw somebody asked about the tricky bit of the extension of the triangles question. Oh, it's only 6:30. Oh, that is refreshing. Oh, we've done it. Breeze through that one with the FTC. Good times. I need to go full screen again. Those are pretty tall questions today. Does this one fit? There we go. We'll do that. Just about. Okay. Yeah, there we go. Okay, happy? Ready? I've scrolled down to 4. 3 got some votes as well. Maybe I was supposed to do 3. I've circled 4 on my... No, we'll come back. We've got time. 5 and 6 worth talking about? Hardly. We're playing a new version where I get to choose. Right, okay. So we've got the function. It's the one I drew before, actually. It's got these triangles, up and down, up and down, up and down. We could write down expressions for what those are. In fact, if you've already done this question and you're at a loose end, challenge. Please could you write down 1, 2, 3, 4, 5. Write down 5 functions, 1 for each of those straight lines. You know how to do that, right? Straight lines, a point on each of those lines. If you really have to, you can write them all down. This is a fair task. I have already had to do this because when I drew the diagram for this worksheet, I had to work out the function, right? Because in my software, I have to tell it what function to plot, like in Desmos, right? I have to tell it what to plot, which meant I had to work out the expression. Or I could have learnt to use like the triangle feature where I tell it the triangle, but I thought I'd work out lines. There's a request in chat for year groups poll. Actually, I'm kind of interested as well, so we're gonna set that up as well. The years are going to be. If I was really cool, I would do this in a way that's not so England specific. I don't think I'm that cool. So England or equiv. Really sorry to I can never quite. I should just know because it comes up quite a lot in my job, but I can never quite remember. How the years. They're out by 1 for Northern Ireland compared to England. I can never quite remember which way around they're out by 1. I think it's 14. I think 14 is school leaving, so I can count backwards. And then I know Scotland had S5 and S6, so I can work back from there. That's great. Let's go S5 here. And then people can correct me, and then if I'm wrong, then I've learned a thing. Can I be bold and extend downwards? Okay. For the function on the question, we're asked about g of x as well. G of x is a sum. It's using this sigma notation, which means to add things together. We've seen this before, actually. We've seen something where there were 8 things added together, and I looked down the barrel of the camera and said, 8's not that many. We can handle 8 functions. And now it's my time for me to stare down the camera and say, 10's not that many. We can handle 10 functions. And I don't know how much I really believe that, but I do know that we can handle the first 2 or 3 and try and spot a pattern. When I say all 10 of them, if we have to, we can work out we've got these 10 things to integrate, because integral, you can split the integral over these separate functions. Oh, have I put that on the notes? I don't think I have. Let's put it on screen now. Medium important fact. If you're asked to integrate f of x plus g of x, I know it's f and g in the question, but forget about that for a second. You can split them apart like this. Is that one of the things that I told you in the revision notes? Did I remember to tell you? That's not the revision notes. Did I remember? Yes, I did remember. That is in the revision notes. Hooray! I put big brackets around this one just to keep it all together. Oh, brilliant. I'm pleased I thought of that. That's in the revision notes. You already knew this. So this G with 10 functions put together. My poll is ready, and I'm probably about to learn that I've gone out by 2 on Northern Ireland. Sorry, Northern Ireland. I'm also going to look it up at the same time. So the poll is, which year group were you in as of June? It's now July, but as of last month, maybe the month before. Oh, when does school stop? Northern Ireland school year equivalent. Shifted by 1. Now have I messed up? Yeah, no, I think I'm good. I think I'm out by 1 in the correct way. Okay, the poll is happening. Good. We have a quick look. I'll let them vote a little bit, and then I'll put the poll on screen. I don't need to hide it right now. Okay, so we've got 10 functions. They're all rescales of this graph. We're going to learn about graph transformations next week. But you've seen some scaling already, I think. And when it says f of 2x or 4x or whatever, 2 to the r minus 1, f of some power of 2x, that represents a transformation in this graph. Multiplying by 2 before you evaluate x says that, well, my favourite way to think about this is what happens when you take this new function, f of 4x or something, and you plug in a number like 1. So you take x equals 1, and it gets multiplied by 4 first. The very first thing that happens is get multiplied by 4. So f of 4x will actually work out f of 4. So you're sitting here with x equals 1, and when you evaluate it, wow, we get f of 4. The value that we would have only seen over at 4 is now right here, being f of 4, whatever that was. This is amazing. In fact, any number that you put in gets multiplied by 4 before it's evaluated, which has the effect of squashing down the graph, because we're accelerating through the progress of the graph. We're seeing it faster. You put in a mundane number like 10, and wow, you're looking at f40. You put in 20, you're looking at f80. For posterity, about a dozen people have voted, and they have voted like this. 69% of them are in year 12 or equivalent, and the next biggest group is younger than year 10. Hello. Which means that the GCSE students who are occasionally here, maybe they're saying they're going into GCSE, they make up a smaller group. And then I think because of small numbers, there is like one person here in each of these categories. But we hit all of the categories? Yeah, we hit all the categories. Haha, we've got one of each. Cool. Wow, that's just gone down. Somebody just voted. Which group are they in? You're more spread across year groups than I would have guessed. That's really interesting to me. That's 2/3 year 12 or equivalent. Huh. Cool, right, okay. I'll leave that. I'll turn it off the screen, but I'm leaving it going. Thank you to the person in chat who suggested that. Took me a moment to set it up, but it was good fun. Oh, Dexter, the GCSE person. He's claiming to be youngest, but I don't think you can know, because there's like a couple of people who voted less than year 10, right? Maybe you're one of them, but you know. Okay, good, right. What are we doing? If you're going into GCSE, you probably want a version of this live stream for GCSE students. I don't think we've got that. Right, this is very soon going to be banned, by the way, for people. Right, isn't YouTube one of the social media platforms that's going to get banned for certain age groups? Right, that going to be. Next time you see that poll, it might be trying to get you off YouTube, which is probably good for you, right? I definitely spend too much time on YouTube. I spent too much time on both sides of YouTube. Here I am. Well, we've hit the existential part of the live stream. It is 20 to 7, and we've still got to do this TMUA question. I spend too long on both sides of YouTube. Beth, help. Beth. Right. There is maybe a bias with Slido. Yeah, that'll be interesting. Stream watchers. There's a different number of people in each of those. And lots of people who join us over the weekend. If you watch over the weekend, you can watch in double speed, and you can skip through all of the bits where I just go weird and don't write anything on the board. You can tell I'm just chatting because you can see my hands, and you can see the screen's not doing anything if you do a 10-second skip. The only YouTube live stream that gives you advice about skipping the stream. What am I talking about? I'm talking about squashing triangles. You squashed a triangle down so that you could find what was going on. You got f of x, which does this, even numbers. Nice. But then f of 2x, let's make it spikier. I've got these squares, I should be using these squares. F of 2x is sort of squashed like this, because when you go to put in the value of x equals 1, it works out f of 2, which was over here, right? Already over here, is now being shown over here. If your job is to integrate from 0 to 1, you are interested in finding this area. And as I hinted before, you're allowed to know how large triangles are, the area of a triangle. You don't have to use integration if you don't want to. Right, so if I integrate this one, I get, well, that's a triangle with width 1 and height 1, so it's got area 1/2. And then this is a triangle with base 1 and height 1, so it's got one area 1/2. Interesting. And then the next one, f of 4x. Rachel in chat says that they've got a number which is not one of the options. I actually quite like it when I get a number that's not one of the options. If I get a number that is one of the options, then I don't know if I'm right or wrong. If I get a number that's not one of the options, then I know I'm wrong. So I have another go at the question. Yes. And at this point, if we're just doing questions to get better at problem solving and to learn a bit more about the maths that's on the specification, apparently loads of us are here to learn A-level maths before you start GCSE, which, you know, if you want to. While we're doing all that, it's probably good to just have another go at the question and find out, you know, opportunity. I think this one's 1/2 as well. But it's two triangles, right? Each of them has got base 1/2 and height 1, but then between them they add up. There's a fun fact here that if you have, maybe this is a sort of magic trick or something. It's not a very good magic trick. You have some unknown number of triangles. You can even go over here. Unknown number of triangles standing on the interval from 0 to 1, so that they divvy up the interval from 0 to 1, and they've all got height 1. The sum of the areas of those triangles, including this weird one that goes over there, that's not really a function of x anymore, is it? But including this weird one that goes over there, the bases add up to 1, and the heights are all the same. So if you wrote down expressions for their areas, they'd all have the same height, which you could factor out. I mean, it's 1 here, but you could, say h. You could factor out a factor of h for the height. And then you're just adding the bases together, and the bases add to 1. So the total here is always 2. Because the bases add up to 1. You know, base plus base plus base, but all of these, 1. Base. Oh, anonymous. There is a bit of UK law. So I did a joke about it a moment ago. Sorry, I think it was a joke. There's a bit of UK law that is maybe going to happen, which is about under 16s and social media, and YouTube counts as social media. So possibly under 16s will not be able to watch YouTube, including this. And then the joke question in chat is, will they be able to get on Slido? To which the answer is hilariously yes. If this all goes through, then presumably 16-year-olds will be able to join in with the polls, but not see the questions happen until they turn 16 and they're allowed to watch the video to find out if their questions were on the poll. I hope no one's doing that. I hope no one is sitting in Slido just voting. That would be boring. Right, okay. Yes, okay. Right, yes, they're half every time, and there are 10 of them. So I've only done the first. I've done the first 3, but I've got bored. I sort of confidently said down the camera we could do all 10, but we're not even going to, are we? Because they're all 1/2. It's like this. Is using 1/2 AB sine C for the area of each triangle a viable way to check your answer /J, which I think is joking? No. Yeah, your guess is as good as mine, Peggy. I don't want to panic anyone, especially not under 16s. This seems pretty far away from happening. Okay. Right. And if you're not in the UK, then I genuinely don't know any of this. Yeah, how do they know if you're in the UK? How do they know if you're under 16? How does any of that work? Yeah, it's France. France and Australia have already done some version of this. I don't know who's watching these. Yes, thank you. Other ways to find the area of a triangle. Chat says, can you use Heron's formula? Bye, Dexter. See you around. Okay, I think this is quite fun because, it's an integration question. But you don't actually have to do any integration because you know how large triangles are. Chat is currently memes about how large triangles are, including Heron's formula. Possibly you were at the open day. At the open day, I have a joke where I suggest that you find the area of a triangle, and then I pause and I say, don't use Heron's formula, because there's this thing called Heron's formula that you should definitely not use unless you really have to, and unless you know what Heron's formula is, which I wouldn't really recommend. Right, good. Okay, I think we're going to do another one. Let's do the third one because it caught me out. Let's do some radical honesty. I got this one wrong. I'm going to get it right now. First time I did this question, I got it totally wrong. Not even for a good reason. I just misread it. You see those little mod signs around the X? In the thing we're asked to evaluate, it says evaluate the integral of f of mod x. And I didn't see that because the brackets and the mod signs very close together. And my eyesight could be better. Which is why there's now a hint on the question sheet that says, note that we're asked for the thing it actually says, not the thing that I read. Too late to help myself, but maybe the hint was helpful for you to realise that the thing in the question is that. You were at the open day, the time that one person put their hand up to say they had been thinking about Heron's formula. That is allowed. It's a triangle question. I'm not going to do the triangle question now. I will probably do it on the live stream at some point when we talk about interview questions later on. But the punchline is don't use Heron's formula. That's not the punchline of the question. Okay, we're given some weird information for this one. It is weird, but it means that f of x is positive when x is positive, because if x is positive, then I'm going to divide, and f of x is negative when x is negative, because if it's negative, I'm still going to divide, but I've got to be careful, because dividing by a negative number is just as bad as multiplying by a negative number. and it will flip the inequality. So it's just describing two different cases. F of x is, something like this. Let's go through the origin. It's positive over here, negative over there. Okay, I don't want to work out what that function is. I would like to, once again, avoid thinking about the function as much as I can. Yes, I really don't want to solve for the function. Hard explanation question, find a function that actually does this, but don't want to unless I have to. So we're given this fact, and we're given this fact. And this is screaming simultaneous equations to me. Simultaneous equations because we have two statements, and there are just some random numbers on the right hand side, 4 and 8. What? I mean, it's twice as much, I suppose. Is that good? Is that bad? It's a different thing. But it feels like simultaneous equations because there are two of them, and we have two numbers. So this is kind of the reverse of a standard question, right? A standard question would be, here are some simultaneous equations, what's the solution? Here it feels like these are simultaneous equations, what's the question? What are the two unknowns? I've got two equations. I'd be greedy to try and work out all of the values of f. But maybe I can dream that this could be equations to tell me about two things. And I get to choose what my two things are. I'm probably going to split this up at 0, right? The thing in the question involves this integral from -2 to 0. In my head, I'm still doing the version of the question where I haven't seen the mod signs, which is actually quite helpful at this stage. If I haven't seen the mod signs, then this thing, for me, without seeing the mod signs, that's one of the things that's very closely related to this thing over here. He says, getting out the red string again. Look, it's closely related to this. If I also have 0 to 2 f of x dx. I think, just for the record, I think that is the last appearance of the red string. It's something to indicate I've spotted a connection, but it is really ugly, and I've decided never to do it again. What's going on with this one? So this is mod signs around the f of x, absolute value, the modulus function, which seems really scary until you remember that this, all it does is it takes negative values and puts a minus sign on, and it leaves positive values alone. That's what these mean. Yeah, almost harmless, right? They'll leave your function alone if it's positive, and they'll flip the sign if it's negative. Oh, that's quite good because we know this fact. Because we invested the time in understanding what this means, we can just say that this is -2 to 0. That's the bit where the function is negative, so the mod signs will put a minus sign on that. 0 to 2 f of x dx is equal to 8. And that minus sign, I'm going to bring it outside the integral like this. You can bring constants outside of integrals. That's on the sheet, right? Yeah, that's definitely in the revision notes. Yeah, you can bring out a constant, including -1. Oh, brilliant. These are simultaneous equations. Let's go and solve the simultaneous equations. 3 for positive, -1 for negative. Yeah, I think that works. I think I want to solve my equations before I do that. But I think 6 and -2 are relevant numbers. Yeah, this bit where the function is negative, -2. Yeah, and then you divide it by 2. Yeah, okay, I think your function works. Can you find a continuous function that works? I think you probably can. Okay. No jump in value. I'm playing an extra game with the chat. Okay, so we've called these A and B. This is 4. This is 8. If I add these, I will get the value of B. If I take the difference, I'll get the value of A. Which one shall I do first? I think add them to get 2b is equal to 12, so B is 12, B is 6, divide by 2, B is 6, and if I take the difference, then 2a is equal to -4, so A is -2. At this point I thought I was done, because I hadn't seen the mod signs on the inside, right? That is not actually asking me for simply the value of A, -2. It's asking me for f of mod x, which is complicated. Where am I going to scroll? I'm going to scroll here. Tough. I would like, just for Ginger Biscuit in chat, I would like the absolute value of f to be continuous. In particular, note that f of 0 is supposed to be equal to 0. I don't need it to be differentiable. It'd be nice if you could do that. Feels like you probably can, but seems like work. Maybe you need some hard work. Put a quadratic in each region. Let's have 0 derivative at the origin as well. You can definitely do that. Yeah, you just need a and b to work out. That's only one number. Just use the right quadratics. X squared minus x squared, scale each side appropriately. Now it's differentiable. Good. So this is harder than I thought because of the mod signs, which means that although, no, I've got the limits wrong as well. Although we're putting in negative values of x, the mods in here, the absolute value, will be positive. Because that's what it does, right? It takes negative numbers and it goes, no, I'm putting a minus sign on those and returning positive numbers. I guess I'm going to go like this. It could be equal to 0. Right at the end point, it's equal to 0. Oh, so we're actually evaluating the function at positive inputs. And f of positive inputs is positive. So this is an area. Which area is it? So the integral is an area. It's an area because we're integrating a positive function. I know that when x is negative, f is negative, but when x is negative, absolute value of x is positive, so the function will be positive. So this is an area. If you like, this is f of minus x in this range, which is like taking that function that I had before. Where's it gone? Taking that function, and you know that f of minus x is a transformation by reflecting. Oh, it's not going to let me do a reflection, is it? Come on. No, it's actually not. It's going to retain the scale factor. That's really annoying. Is a reflection. Oh, and I'm off the screen. Is a reflection in the line x equals 0. It reflects minus x. So what was function on the right is now function on the left. And if I want that area, well, I shouldn't do this reflection business. I should just integrate from 0 to 2. That's true in general, actually, even if it's not a positive function, but let's not worry about that. Emma in chat's got there. Yes, 2 to 0, or the negative of the integral from 0 to 2. Is that not just the integral from 0 to 2 of f of x? EJ? Correct, it is not. No, wrong, it is not that, it is that. It's too late for this. Chat saying, see what? Is that not just the integral of 0 to 2 from f of x? So B, no. It is the integral from 0 to 2 of f of x. And it is B, which is the thing I calculated over here. It is 6. My answer was I thought they were asking for A, they're actually asking for B. I solved the equations and then I selected the wrong answer. Fun. Okay, so this is another example where you don't actually integrate a function, you think about areas instead. And this connection between areas and integrals, it's much more interesting to me than just like, can you integrate x cubed? Probably can, because it's on the revision notes. Right, there was a hard question at some point, somebody requested. In the extension activity, there's a suggestion that you can work out an expression for a function that gives that plot. So instead of doing the straight line segments, there is a single line expression that you can give to Desmos that plots the whole thing using two things, two sort of special ingredients. One of them is absolute value of x, which Desmos knows about. You have to use the button on your keyboard that does vertical line, and also using floor, the floor function in Desmos. Floor takes the largest integer that is less than x, which is good. It does this kind of step thing. Between 1 and 2, it just says 1, 1, 1, 1, 1, 1. And between 2 and 3, it says 2, 2, 2, 2, 2, 2, 2, which is good for these kind of like things that change suddenly. 1, 2. Well, that's not quite what we want because it keeps going up. So it's 3 and then 4. B is my my letter B is the number 6, which is not option B, it's option G. So I've circled B, but I mean G. Square. Oops. What a mess. Ooh, Desmos is doing. People are doing stuff in chat is filling up with Desmos. Okay, so you can try and build a function of this. I want to be clear that this function with the up and down lines that exists whether or not you can play this game of building something out of floor and mod x. None of that actually matters. The function just is. There are the values between 0 and 1, up and down. Function to me. But if you would like to find an explicit expression using simple-ish functions that Desmos knows about, you can do a one-liner that produces that plot. Who knows? Who knows? Right, good. Okay, thank you for joining in. I think my job now is to go and fix whatever's wrong with the web version before the weekend, because if you're watching at the weekend, I want to make sure that it's too late now, isn't it? It's kind of a week too late. I'm going to go and fix it anyway. Right. Thank you. That was good. People in chat are posting their Desmos one-liners, which is always fun. Thanks for joining in. I will see you in 166 hours for another episode of the Oxford MAT Livestream. But until then, have a nice evening. Have a nice weekend. Have a nice week. Enjoy your maths. And I'll see you in 166 hours for another one of these. Bye.